speaker today is Professor Rafał Demkowicz-Dobrzański from Warsaw University. So for those who doesn't know Rafał, he did his PhD with Professor Marek Buś at CTP, and then he did his postdoc with Konrad Banaszek, and now he's a professor at the university, Warsaw University. Rafał, please tell us about the unified theory of quantum metrology.
Okay, thank you very much. So I'm really happy to be here, and let me start with the general picture of what is quantum metrology. So quantum metrology is a field where we ask how well we can exploit quantum features of light and matter to perform precise measurements. So by quantum features, one can understand just quantum coherence, or more specifically entanglement, which is some kind of more sophisticated quantum coherence. And if you think about particular implementations, like optical interferometry, then, for example, a standard interferometer that uses classical light, the name that Professor Wielnicki doesn't like, but by this I just mean coherent states of light. Okay, so the states that you can also describe within semi-classical theory, where light is treated classically and just detectors are treated quantumly, and you have shot noise. So you have photons, but on the side of the light, you can describe everything classically, just the detection process has portions of light. I mean by this classical thing. Of course. Yes, but you can equally well describe these experiments with coherent states using semi-classical theory. Okay, this is what. And so if you perform this kind of interferometry, you just use the coherence of light as a feature to measure something. But then you can try to play with your photons in a more sophisticated way, in a way that you cannot describe within semi-classical description. And for example, you can use squeezed states of light to boost the performance of optical interferometers. And such schemes can be viewed from perspective of the photons as utilizing entanglement between photons to improve sensitivity of interferometers. So you have these two levels, and then of course to make some realistic statements you have to take into account real-life noise decoherence, which in case of optical interferometers the most pronounced process is photon loss. Okay. Then you can think about atomic interferometers like Bose-Einstein condensate interferometers, or just atomic metrological protocols like in atomic clocks. And then you can also use coherence, which in this case, for example, for atomic clocks would mean coherence between atoms being in a ground or excited states, superpositions of these states, and use many atoms and play with them. Or you can try to boost the performance by, for example, entangling atoms. So having ions, for example, in trap, a few of them, and let them interact and prepare some entangled states of ions, and in this way boost the sensitivity of atomic clock, for example. And then, of course, you also have a lot of problems with noise. For example, in atomic clocks, the main problem is the stability of your laser with which you interact with atoms, which in the mathematical models amounts to something which can be written equivalent to atom dephasing. And you also have loss of atoms. And then there is a third field which I would distinguish that people are interested in, is solid state implementations. And for example, recently there is a lot of work with so-called NV centers in diamonds, which are good sensors, for example, of magnetic field. And then you can use just, again, electronic levels and coherences between them to sense magnetic field, but you can try to play more fancy protocols like entangle these electronic states with some nuclear spins in the neighborhood, and in this way implement some kind of more sophisticated quantum protocols. Yes. Yes, so this is like single envy center and single nucleus. Yes, but in these experiments you can, in some sense, address single impurities and let them interact with just one neighboring nucleus in this diamond structure. This is yes, this is an electron in this impurity, within this impurity, this envy center. This is like an artificial atomic structure because of this defect in the crystal.
So this electron is not bound.
Yes,
So
yes.
the difference between the atom and this, I mean, it's artificial atom.
Yes, yes, it is. Yes.
Has anybody looked at this effect in just an atom?
But here the advantage is that we have very good optical properties of this impurity, so that's why it's being used. And okay, so this is just an overview of like different approaches to physical implementations of quantum metrological protocols. But now I will turn to like more abstract approach from a theoretical point of view, and the whole field of quantum metrology can be viewed as a special case of quantum channel estimation problem. So you have some dynamics, some evolution of quantum system that depends on unknown parameter phi, and you prepare your input states, you evolve them, and then you measure this output state and obtain some measurement results I, based on which you try to estimate this parameter. And this last thing is so-called estimator. So this is a function of measurement results that returns. You don't know phi, but you usually know the structure of u.
So how do you know there is a phi there?
How do I know?
That there is a phi.
Okay, I have a model of interaction of my physical systems.
In order to construct the P sub I, you need to have some knowledge.
Sometimes yes, but not always. But of course you can think about this process in like adaptive way. So for example, first you enter your lab and you measure this phi just roughly, and in this way you know more or less what is this phi is.
There is a certain operator U which
Yes.
there is a physical device which has some internal degrees of freedom.
Yes. So for example, this atom or this impurity.
This up to that point I understood that then you have it. What is then P sub I?
This P, these are your measurement operators. This can be like projective.
Measurement operator measures something.
Yes. So, for example, occupation number.
Do you know that the output of these measurements has anything to do with the phi?
Because I have a model of this process. Of course,
You know what is phi.
for example, it can be magnetic field, but I don't know its value. I know what is it physically, but I don't know its value. I need to have a probabilistic model. In this way, I need to understand what's going on in my system, but I don't know the value of one parameter within this model. You can think like this. Magnetic field, for example.
Otherwise you would be unable to measure.
Of course. Of course. Okay. So then a goal for a theorist is to take this scheme and minimize the variance of your estimator. So to have an estimation which gives you as close values of estimated values to the true values. So minimize this variance over your measurements, estimator function, and your input states. So these are like three things you have control over. Okay? And now the question is how good you can do it. And the tool that is very, very useful in this field is so-called Fisher information, which enters through the so-called Cramer-Rao inequality, which on a just within a classical picture tells you that if you have some probabilistic model where you have these events I that depend on the value of phi, so you have some probability distribution of different events I, and then you can design any kind of function of estimator function, phi tilde as a function of I, then the Cramer-Rao inequality tells you that provided you want to have an estimator which is unbiased, which means that on average it will give you the true value, you can never find an estimator which gives you better estimation variance than inverse of Fisher information. And Fisher information is a function that depends on how this probability distribution how quickly this probability distribution changes with the variations of phi. Okay? We don't assume anything. We just assume unbiasedness. No, but this is a single parameter estimation. There are many measurement results, but single parameter. Okay? If there were more parameters, then true. But this is single parameter estimation.
So you do several measurements with different P of i's measuring the same theoretical value.
I have the same set P of i's, fixed set P of i's and different i's.
Stick with this, what you said about the magnetic field. Okay? That depend, you don't know the value of it.
Yes.
So you do several measurements to measure the value of the magnetic field.
No, I measure this, for example, spin orientation of my atoms that interacted with magnetic field, and I had Larmor precession and so on.
How the device work, but the spin orientation is not the magnetic field.
Of course.
Point about the value.
So I have a model. Yes.
Can I finish?
Yeah, but I think I know the answer to your question.
Well, that is tremendous result of a Cramer-Rao. Answer to the question if you don't know the question. That's remarkable. The point is that you told us that you have to measure the value of a magnetic field.
No. I told you that the phi is a magnetic field, and then I measure measurement of
I is some device via which I measure the value of the magnetic
indirectly, which means that I let atoms.
Example, when you want to find a mass of something, you can use gravitation.
No, but
Yes, and to measure the length of the screen.
okay. So the simple. Okay. Can I answer you one sentence? So imagine I have a spin 1/2 atom or particle which precess. Yes. Let me finish. Now let me finish. Which precess in magnetic field. Okay. And in this way, by measuring projection of the spin, for example, on the x-axis, while it precesses around z-axis, I can measure the strength of magnetic field, because the stronger is magnetic field, the faster the precession is. And in this way, I can infer.
What is the label I?
In this case, it will be plus or minus 1/2 projection on an x-axis, which is, for example, repeated over many atoms. So I'll have a collection of i's, because I, for example, measure n atoms which precess, and from this I can estimate what was the angle that the spin traveled in this magnetic field. In this example, I project spin of an atom, which is coupled to magnetic field, and in this way, indirectly, I estimate magnetic field.
The experiments in whatever sense
Yes.
in order to measure the value of the same quantity.
Yes. Yes. But I can also think formally in this way, that this index I is like a large index with many values, and I have a single measurement.
It is discrete.
Yes. It can be, but it could be also continuous. It's continuous.
And the value of this derivative is taken in the actual,
At the true value.
which we don't know.
Yes, which we don't know, but I can calculate this quantity. I can know how sensitive I would be if I were at this value.
But how do I evaluate such a derivative?
Because I have the model. I have this probability distribution from my model. Okay?
So the PI phi, this is a theoretical idea.
Probabilistic model of my physical experiment.
This is an idea of that outcome of the experiment.
Yes. So now, okay, now let me explain it in detail. Look here, please. So this was like just pure classical theory. You could say that you have this probability distribution from somewhere, not necessarily from quantum model. Okay, and now you say that, okay, this what I have is actually a measurement pi I performed on this output state psi that depends on phi, because it evolved through this channel that depended on phi. Okay? And now I put this into here, and one can prove that now you can show that whatever measurement now you choose, you cannot do better than the bound where FQ is so-called quantum Fisher information, and there is no measurement at all there. Because you optimize over all possible measurements, and you can prove that you cannot do better than this, where this is quantum Fisher information that depends on the state.
The question is, how do you calculate this derivative in the lower? I mean, you said that C dot is a derivative in the space. Then you don't have any model.
No, I have a model of U phi.
You have this state.
Yes, but I also have U phi that depends on unknown parameter phi over which I take derivative.
Well, maybe it doesn't have that parameter. That might happen.
Then it's zero. Okay. That Fisher information is zero, and I cannot infer anything.
You cannot measure that. If this U does not depend
Okay.
on magnetic field, you cannot measure.
So to give you an intuitive correspondence between this and time-energy uncertainty relation. So think that you have a quantum state that you evolve under some known Hamiltonian, but for unknown time. Okay? So you have this output state, and from the output state, you want to infer how long this state evolved. And then this formula amounts to the fact that Fisher information in this case will be 4 times the variance of this Hamiltonian, which means that you cannot estimate the time better than 1/4 variance of the Hamiltonian. Okay?
Can one disentangle mathematics from physics? What is precisely the mathematical statement here which will ignore completely the physical background?
Okay, but of this?
Yes, for example here.
Of this, you need to say that I have some unitary evolution generated by some Hermitian operator multiplied by this number, which I want to estimate. And then I have this vector on which I can perform arbitrarily measurements.
Let's forget about the measurement.
No, I have to say about measuring things.
Mathematics here. Pure mathematics.
Okay, so
Measurements is very
measurement is described as a positive operators that sum up to identity. Not necessarily projected, they can be this generalized measurement as well. So I have this P of M, this generalized measurement, positive operators that sum up to identity, and they have indices, which are my measurement results, and I...
even say that in statement that something is measurement is very the physical information here is very small. I mean, this is,
Oh, but
yes, this is purely mathematics. This is purely mathematics.
okay. Okay, so for example, now to give you again example, you can think of a qubit or a 2-level system, which is described, which you can think about as pictured on a Bloch sphere, and estimate the angle of rotation around the axis. So this would correspond to this precession within magnetic field. So you can think that phi now is magnetic field, and you have rotation. Okay, and within such model, you can derive this Fisher information very easily. And first, you can consider something which I would call uncorrelated scheme. So in this sense, every qubit or every atom, you evolve independently and you measure independently and you repeat it n times. And then you can contrast this with like a more general quantum scheme where you allow these n atoms to be prepared in arbitrary entangled state, evolve them through these channels and perform like collective measurement on all of them. Okay, this is what I would call entanglement enhanced scheme. And now you can ask the question, okay, so what input states I should send here to maximize the quantum Fisher information, to know what is the limit for precision. So in this case, it's very easy because I just need to consider like single channel because quantum Fisher information is additive on product states. That's why it deserves the name information, because it's additive. Okay, so then I just need to look for a single qubit state that maximizes this Fisher information, and not surprisingly, it's any state on the equator of the Bloch sphere because it rotates the most. Okay, and the Fisher information is 1, so if I have n channels, it's n times 1, it's n. Okay, but then if I have this scheme, I can consider more general states, and I can consider this entangled states where n qubits are in 0 state plus n qubits are in 1 state, and then this relative phase is acquired n times faster, and then you can, from this formula, you can easily see that the Fisher is n squared, because you have this derivative over n squared, and that's why it's n squared here. So you have the so-called Heisenberg limit versus standard limit in precision. But actually this scheme that I described here is not the most general scheme you can think if you just say, okay, I can do anything, but I'm allowed just to use these gates n times. Okay, so this unitary is like a single resource that you have, and you are allowed to use it n times, but apart from that, you can do anything quantum mechanics allow you for. And therefore, you can construct this kind of schemes, which I refer to as general adaptive scheme, because this is the most general way you can probe this n gates. Okay, okay, so
This is something like a time space.
okay, so maybe to give you intuition. So I can recover this scheme within this scheme if these VIs are unitary operations, arbitrary unitary operations. I can, for example, make them like swap operations that make this line go here and this line go here. And in this way, I would go back to parallel scheme, because I can make every of these lines go through a different U. Okay? But this structure is much richer, because in principle, I can use arbitrary many ancillary systems here. There's no limit here. It's just the limit on the number of gates, but no limit on number of particles I use here. And therefore, I can use some of these particles, for example, to make some entanglement between this state that will go through the gate and some ancilla. Then I can measure ancilla in the end, and in this way I can implement adaptive schemes where, depending on the measurement result, different unitaries act within this scheme and change the input state that will go into the next channel and so on. Okay, maybe it's not obvious from this structure, but it is.
That's no central state.
But I just want to say that this is this comprises all schemes in which you are allowed to use these n channels in arbitrary way. There's nothing more general. So you have to believe me if my explanation is not clear enough. Okay, and interesting thing happens that even though this scheme is very general, it does not give you bigger Fisher information than this simple parallel scheme. It gives you n squared again. So there is like no real gain in considering these more general adaptive schemes for this problem of unitary parameter estimation. Okay, and now I was discussing phase estimation, but what I want to focus in this talk is frequency estimation, which is very closely related because we just replace phi with omega t, and we think that we want to estimate omega, and t is given. So we know how long we evolve, but we want to estimate frequency. So this would be a situation in which we want to estimate, for example, the level splitting in atoms or something. And everything is the same, but now you have to remember that because we want to estimate frequency, we can adjust the time of each single gate as well as we want, for example, to make them short or long. And therefore, it's not reasonable to fix n as a resource, so number of gates, but rather fix total interrogation time of my gates as a resource. Okay? So here the number of gates is capital T over small t, but you should think that the total interrogation time is your resource. Okay? And then you ask how well you can estimate omega. Okay, and just using the previous result, where you had that the Fisher information was like n squared, in this case it's t over t squared, then you can immediately say what is the Fisher information for estimating omega, because you just apply like a standard error propagation formula where you just multiply this. Fisher is like an inverse of variance. So inverse of variance for phase. If you want to have inverse of variance for frequency, you have to multiply it by this proportionality factor t squared.
What are the units in which capital T is measured?
Seconds. It's
The result depends on the units.
No, but this is frequency here. Yes, you see, because I introduce my parameter as a frequency, because it multiplies time.
I'm talking about this f of omega.
Yes, this depends on unit because it's Fisher information of estimating parameter omega, which has units, because it's frequency-like parameter, and then it should be second squared because it's inverse variance of frequency. Okay. Okay.
And T is a number of,
Capital T
yeah, the capital.
is the total interrogation time that I used. I used this evolution for this long time. I could inter.
Yellow inequality says in simple terms that the error in measuring the frequency in this very complicated scheme is larger than the inverse of the time.
We interrogate the system. Yes. So it's okay. So it may be obvious statement, but it's not so obvious because we have very precise meaning of what is delta omega here and what kind of schemes we consider. That these are the most general schemes like this.
That follow from a simple analysis of the circular motion.
Okay, if you consider, yes,
The same results in classical physics and pendulums.
for particular models you would get, and here, no,
It's the results
okay,
of that model.
but you see here.
For that U, there will be a different U.
But you see, this is quite a general model. The U is fixed, but I'm allowed to build around it arbitrary structures. And still this does not change.
Use arbitrarily complicated device to measure the frequency, and that is irrelevant. It's a question whether the result, I mean, there is a physical quantity I want to measure, and I repeat whatever complicated measure, and that I think is a completely classical result.
I would not agree with this, but okay.
Well, it is a classical because the H bar does not consider. So if the H bar is zero, these results will follow.
Okay.
Is it so obvious that this classical result immediately translates to this scenario? Because here
No, I think that whatever it says is, I mean, I'm looking at this average.
Okay. Of
I'm measuring the frequency of precession or rotation, right? Or
Yes.
which is the same physical quantity as the frequency of a
you are referring
There's no,
to properties of Fourier transform, okay? But okay.
and so then the question is like,
Yes. You are referring to properties of Fourier transform, but
it's remarkable that we get the classical.
it's more general.
There was this
Yes.
argument that we start from a particular state that was
Yes.
in Fock states.
Okay.
We need to accumulate a phase difference of order of 2 pi between two states which have the minimal energy difference. And basically, if I were allowed to replace 1 by 2 pi, that would be this argument.
Okay, you can have a lot of variants of these things, but a lot of them are not fully general and do not have really very precise operational meaning, I would say. And this has very precise operational meaning.
This idea, I'm trying to understand that there is something very peculiar that you get this result. I mean, I was expecting something very different.
No, but okay, but this was introduction, okay? Because now everything was for unitary evolution, okay? Yes, and now interesting things happen when you take into account decoherence, so the fact that you don't have unitary evolution, okay? So now you replace unitary channel with so-called completely positive map, so general description of how quantum states evolve that are in contact in environment, okay? And for example, in case of interferometry, this will be replacing interferometer with lossy interferometer. In case of, for example, this atomic precession, you would add dephasing of atoms that destroy coherence between levels. And now the same question you can ask, but replace this U with these maps. And now the question is far from trivial because you have mixed states, and calculating Fisher information for mixed state is a challenging task. And a priori, you cannot answer this question. What will be the maximum value of Fisher in this case? But now there is, so now you have to understand the structure of the Fisher information for mixed states. So imagine you have raw mixed state evolving from this noisy channel. You get some mixed state at the output. And now there is an explicit, in some sense, explicit formula for quantum Fisher information for mixed states, but it's not so explicit because it involves an operator, which is called here A phi, which is called symmetric logarithmic derivative, which you have to solve by solving this equation. So you again have a derivative of your density matrix, and now you have to find an operator that gives you the derivative when you calculate anti-commutator of it with your state. Okay? And it's called symmetric logarithmic derivative. Okay? And you can of course do it, but in general you need to diagonalize your density matrix. So you can do it numerically for small dimensions, but in general you cannot solve a lot. Okay? But there is a very beautiful theorem.
Is A unique?
It's unique if rho is full rank. If it's not full rank, then it's not unique.
What means full rank?
So if you have d-dimensional quantum system, the density matrix has d non-zero eigenvalues. If you have d-dimensional quantum system, density matrix has d non-zero eigenvalues. So d larger than zero eigenvalues.
They must be different also.
This I'm not sure. No. But here it's important also the derivative. So maybe if you say that you have both rho and its derivative, the degeneracy in the same space, then probably yes. Probably then you will have freedom. Because you have two operators here, rho and d rho over phi.
Yes, I see that, but if there is a degeneracy, I would be doubtful that you have unique A.
But if rho is degenerate, but d rho over phi will not be degenerate within this subspace, it could be. If it is, then indeed. But then it will be like trivial, in this subspace will be trivial, because there will be no information in this subspace. Okay, so that's in a sense trivial. But there is a very, very beautiful theorem which tells you that if you want to calculate quantum Fisher information for mixed states, you can think about a purification of this mixed state. So think about mixed state, but think that this mixed state is actually a reduced state, a subsystem of a bigger system which is pure. Okay? And then, of course, if you think about a bigger system which is pure, you have more information if you had access to this bigger system. So the Fisher information of a purification of a given mixed state will always be larger. I mean, no smaller than this mixed state. But then you can think about performing minimization over all possible purifications. And the theorem is that if you perform this minimization, you get equality. So there is a purification which does not give you more information than the actual mixed state. Okay? So this is very, very nice theorem because it may be helpful to derive bounds. Because, okay, so the intuition is like this. If you can find a clever purification that gives you a quite tight bound, you can calculate Fisher information for this purification easily and get a useful bound for the mixed states. This is the idea.
That there is always the case which
Equality. Yes, it is proven. Okay. Yes, there is always such purification. Okay, so now I will just give you the idea of our use of this fact to derive bounds for this evolution with noise, so with decoherence. So you can think about these quantum channels again as your system interacts with some environment, and that's why you have decoherence. If you have this general quantum channel, this K are called Krauss operators. You can also equivalently define another set of Krauss operators which are related to these Krauss operators by an entries coming from a unitary matrix. So these Vij are entries from a unitary matrix. And you can show that if you replace this K with K tilde, the channel does not change. So the Krauss representation is not unique. And actually this non-uniqueness of Krauss representation of a quantum channel is like very closely related to non-uniqueness of these purifications of mixed state. Because you can also always perform some unitary rotations on environment, changing the basis there, and it does not change your density matrix because you trace out these additional degrees of freedom. But the trick here is that with these ideas, you can derive the bound on this Fisher information for this mixed state as a bound which is expressed explicitly thanks to the fact that we minimized over different purifications of our channel, different Krauss representations of our channel, which corresponds to different purifications of our evolution, for which we could calculate Fisher information explicitly. So I'm not able to give you the reasonings, the steps of the reasonings. I just give you the intuition that, that this is the main idea here. To purify your dynamics and minimize over different purifications, which in this case amounts to having some formula which is quite easy to calculate, and I will just explain it in a moment, but you minimize this formula over Krauss representations of your channel. Okay, and what this formula contains. This formula contains n, which is like number of uses of the channel, and then you have some operators alpha and beta, and these alpha and beta operators are constructed from Krauss operators of this channel. K dot means derivative over the parameter for this Krauss operator. And this is operator norm of these operators. So even though it looks maybe not so trivial, the really nice thing about this formula is this, that alpha and beta are operators which are written in terms of Krauss representation of a single channel, just one of these boxes, okay? This is crucial in this formula, that you are able to tell something about this whole protocol, which involves all this entanglement and so on, and you do it by just studying the structure of this single channel in this scheme. So that's the beauty of this formula. And now if you look at this formula, you will now see that you have the term that scales linearly with n, and you have a term that scales quadratically with n. And if you are able to find Krauss representation for which this quantity is 0, this means you will prove that Fisher information cannot scale better than linearly, so that you cannot have this Heisenberg scaling, n squared. Okay? So this is the power of this bound. If you can find beta 0, then you show that you cannot reach Heisenberg scaling within the most general quantum scheme. Now you can translate this bound, this was like for phase estimation. Now you can translate this bound for frequency estimation, which is just this trivial step I described before. You just change your resources from n to capital T. Okay? So for example, you have, again, estimating omega, and you have some dephasing with dephasing rate gamma. So the Bloch sphere shrinks with parameter eta, which is E2 minus gamma t. Okay? And again, you ask the same question. And now you will be interested in answering whether Fisher information can scale linearly with t or quadratically with t. Okay? So you do the same thing as before, but now you can try to give like a broader answer to this problem, which will be valid in very general situation whenever you can describe your problem using this quantum master equation, the so-called Lindblad equation, or in Poland we call it Kosakowski-Sudarshan-Lindblad-Gorini equation. So you have the evolution of a quantum system under Markovian noise can always be described like this, where you have a unitary part, and in our case, this unitary part contains this parameter we want to estimate, this omega, and then you have this noisy part where we assume that noise does not have parameter dependence, okay? So there is no parameter we want to estimate in the noise. So this is the assumption. So noise is just bad thing we want to protect from our unitary dynamics. Okay? And this L are noise operators, and this is like the most general form for evolution of quantum open system under assumption of Markovian noise. Okay? And And now we can write this bound that I showed you before for phase. Now we can write it for frequency, which just means we replace n by capital T over small t, because this is number of uses of the gate. But now also this alpha and beta parameters, they depend on t, because I can change the duration of my channel action. Okay? Yes, mean is over a whole thing. Yes. And now there is this beautiful simplification which we get because we consider frequency estimation. As I told you before, we here can adjust this small t as we want. Okay, this is like optimization parameter. But now, since this is like the most general adaptive scheme, it means that in particular these V matrices can be identities. Okay? So it's always more general to assume t go to 0. Because this is like more gates that are, we have more like freedom in these adaptive strategies. Because we slashed it more densely. Okay? Yes, exactly. So this is, we will not lose optimality. We can only win. Because we can always say, okay, we put these V's identities and I prolong the evolution.
But the question is, does the limit exist?
Yes. Okay, so now we have to study this quantity, taking this limit t to 0. Okay, but this is really a great thing for us, because now we have this Lindblad equation where we have this noise operators and Hamiltonian. And because we go with t to 0, we can immediately write the first order expansion of Krauss operators that correspond to this. And we don't have to solve the evolution, we don't have to integrate the dynamics to get like this proper channel. We can just expand it to the lowest order, and because of this, we will be able to answer this question in full generality just by seeing what are the operators that are in this Lindblad equation. Okay? And then I will again spare you this derivation of this expansion.
How is K0 different from Kj?
So if you derive this Lindblad equation, you always have like you can always split your Krauss operators in this way, that one Krauss operator starts with identity, because you need to have, when t goes to 0, you need to go to a map which is identity. It has to be a trivial map when t goes to 0. That means one of these Krauss operators has to go to 1 to have this trivial limit.
So every time you are doing this, you are making some error. So do you know, can anyone check if you add up all those errors?
No, okay.
Will not contribute anything?
No, because I know that I can expand this to this order, and my evolution will be correct if I have this t going to 0, this bound. I mean, this order will not matter in this bound. Okay. Yes, in this limit. Okay, so again, I spare you these expansions, but I just mentioned the end result, which is very nice, because it's just a pure algebraic statement about relation between Hamiltonian, which gives you this parameter generation, this unitary evolution related with the parameter you want to estimate, and this noise operators. And this statement is the following, that if you consider such a space which is spanned by your noise operators, H is the Hermitian part of the operator, AH is anti-Hermitian part. So we want to construct Hermitian operators out of these noise operators and their products. Okay? And identity. So this is like a space of Hermitian matrices constructed from these noise operators that appear in this Lindblad equation. And if you see that your Hamiltonian is inside this space, then you can show that there is no way you can protect your system from decoherence in a way that you will have t-squared Fisher information. You will always have scaling of Fisher as t. So, for example, arbitrary quantum error correction tricks or different stuff will not help you to make t-squared. It will always be t. Okay? And we have also a way to calculate this constant here, but I will not discuss this. So what is the consequence of this? I should be finishing, yes? In what? So 1 hour. It's 1 hour. Okay. Okay. So first message from this formula is that this Heisenberg scaling, typically, if you take a random noise model, will be lost. So typically, this condition will be satisfied. So for example, if you take this dephasing, okay, what are the corresponding operators? Hamiltonian is just sigma z, because this is the rotation around z-axis. And because the dephasing also is along the z-axis, this noise operator is also sigma z in this model. So of course, Hamiltonian belongs to this space.
What about the magnetic field, which is
Exactly. So I will have this example in the next slide. Yes. Yes. So in this case, you immediately can infer that there will be no better scaling than Fisher information going like linearly in T, which means that precision of estimation will scale like 1 over square root of T, and you can even derive the exact constant here. Okay? That you cannot beat this limit for estimating omega. In case of interferometry with losses, you can proceed in a similar way. Okay, maybe I will skip this because here it's a bit tricky because you have to think about your photon as your elementary system. It can go along both arms. These are like ground and excited level of an atom, but then you should add a third level which represents that photon is lost. Okay, so formally you would describe this process in a three-dimensional space where these loss operators are transferring the state of this photon from these levels 1 and 2 to the level 3, which is this vacuum. But anyway, you can also see here that this Hamiltonian will belong to this space because you see here, you have these products of L operators. So from product of this L with itself, you can make an 1 on a diagonal. And also from this, you can make a 1 on another on this middle point on a diagonal. So from there you can write Hamiltonian as a linear combination of this of such terms. Okay. And again, you can prove the bound in a quantitative way that your scaling is never better than this. So these are bad news that typically you lose Heisenberg scaling. But it does not mean that you don't have any advantage from quantum entanglement and so on. You have an advantage because these constants are actually not reachable by standard schemes. You need to use some quantum input to reach these bounds. And for example, you can reach these bounds in optical interferometry by indeed using squeezed states of light.
These are mathematical inequalities, right?
Yes.
Yes. Mathematical equation, and within this language, how is delta omega defined? If you just know the Lindblad equation, where is the definition?
So delta omega is strictly speaking this estimator. This is estimator of omega, and this is a bound on how well you can estimate omega. So this is a bound on any unbiased estimator.
No, that I understand, but within this framework, we have some Hilbert space.
Yes.
Et cetera, and how in this language you define the mathematical formula.
It's an estimator function. So okay, maybe it's an abuse of notation because here omega is a parameter, scalar parameter, which I want to estimate. And strictly speaking, here it's an uncertainty of an estimator of this omega. Okay. I could write tilde here to represent the fact that it's a bound on estimator, but. But I think that it should be, clear.
Again, what is the formula for delta omega which you use to
okay. So the formula for delta omega is just that if I have these different measurement results I that I can obtain, okay? So no, but this is important. What is the mathematical formula? Okay, so the variance the variance of this. Okay, so you remember this, we had this probability of different measurement results depending on phi, and then you have this, oh sorry, omega, here omega. And then you have, okay, so maybe I write with this tilde to make it clear. And then you have the estimator, what I estimate if my measurement result is I, and I subtract the true value of omega squared, okay? So this is like the variance.
I know the solution of this equation. Suppose I know the solution. How do I find delta omega from the solution of this equation?
Okay. No, you don't, yes.
It's worth stressing that there's another ingredient apart from quantum mechanics here. There's some kind of probabilistic space in which all
Yes, okay, but it's generated from quantum language. It's just, okay, I just say that this statement is a statement about, it's a bound on this quantity with assumption that this estimator is unbiased, furthermore. So unbiasedness means that if I sum over all measurement results, if I sum this estimator, it will give me the true value.
So what is the
This is unbiasedness.
in terms of rho?
This? So this was given. This is just,
So in addition to this structure,
this is this trace.
some additional operators, right?
This was this measurement, this generalized measurement acting on my state. Yes, this P of UMs, yes. This comes from here. Which are hidden because this is already optimized over this P of UMs. Because this is this quantum Fisher information which already did this optimization implicitly.
Am I correct that in the human language that expression means that whatever you do with measuring frequency, you will not do better?
Yes, 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 yes.
Something is just said that whatever you do with the physical,
Okay. Yeah. Okay. So to give you, to finish this last 5 minutes with some fancy news, fancy information, I should just mention that this is not fiction. So this bound that tells us that you cannot do better than this is actually almost reachable in practice in gravitational wave detection, where you indeed people. They did use squeezed light in this small gravitational wave detector near Hanover, which is like kind of test bed for fancy technology for gravitational wave detection. And they showed that, that if this is noise and this dashed line is a model for how well they perform using their squeezed states of light, this solid line corresponds to the bound. So that if even they squeezed more and had, methods to produce arbitrary states of light, they could not beat that solid line. So actually they are very close to this limit that I described. Okay? Why are they close? Because they have high losses. Okay? So in this sense, under a given level of loss they have, which is like 30-something%. So a photon is lost with probability 30%. They cannot beat this coherent light interferometry by better than like, again, 30-something%. This is like the ratio they obtained. The reduction in noise in estimating like phase, if they use squeezed light compared to coherent light, this is like 30-something% reduction. Okay, this is this reduction from this gray line to this red line. Okay, but it's not maybe a huge improvement, but it's observable improvement. And that's why, indeed, now, this year, this squeezed source of light is being implemented in LIGO itself. And next year, detections should make detections using squeezed light. So this will be, I think, a huge event if they eventually will report that we've detected a source of gravitational wave detection using squeezed light. I think next year you can expect such a news. Okay, so I have just 5 minutes, so I will just mention now the theorem that goes the other direction. So this is what Professor Turski was asking. So if this Hamiltonian does not belong to this space, does it mean that you can always protect yourself from noise and recover this Heisenberg scaling, this t-squared scaling. So if you consider, for example, now perpendicular, we call perpendicular dephasing. Okay? So rotation is around z-axis, but the noise acts in a way that it destroys coherences, but it acts along x-axis. Okay? Then you can clearly convince yourself that this condition is not satisfied. Because by multiplying L times L, you get identity. You cannot write sigma z as a function of sigma x, identity, and products of sigma x. Okay? And indeed, there were some papers that studied this model, and they realized that you can reach this t-squared. And there is a simple quantum error correction inspired scheme to reach this, which uses just 2 qubits, 2 entangled qubits. But I will skip this because if somebody is interested, I can tell later, but I don't have time. But it's really a simple 2 qubit scheme.
If I have a Helmholtz coil which is slightly bent, then the fluctuating field is always in this z direction, y direction, whatever. Then all this you were talking previously is not applicable.
Okay, so
We are lost, right? Because we don't have any.
you mean that I require here strictly that sigma x?
No,
No, it can be any angle which is not sigma z actually.
physically, I have a coil which generates a magnetic
Okay.
field. Which generates
Yeah. Yes.
It's perfect.
Of course.
Then it on the value of it fluctuates, but if it's slightly bended, it generates
Okay.
a z component,
So-
y component, and they mix.
Okay, so as you can see, I'm not a co-author of any of these papers because I know, okay, this is Janek Kołodyński, my PhD student who during our PhD, he said, okay, let's consider this model. And I said, oh, but it's not really physical, okay. But he did, and he wrote papers. And some people are thinking that in some situations you can have this situation. Okay, so this same statement will hold if you have a single L which is not sigma z. Just slightly in other direction. It can be sigma n, with n it's a vector which is not pointing in z direction. Oh, I mean it's great if you were able to achieve it. Okay, so now finally I should mention this general theorem. So this was the example, okay? So now, maybe I just last sentence. So actually this example is an illustration of a more general theorem, which states that whenever this Hamiltonian does not belong to this space, you can construct something like quantum error correction code. And actually, unfortunately, we did not manage to do it ourselves. It was done 3 months after our paper was put on the archive by another group, where they explicitly constructed this quantum error correction code for any case like this. So provided this is satisfied, you can construct this error correction code and get this t-squared scaling. Okay, and this is the construction, which again I will skip, and I will skip this many body things. I just mentioned that we have done something with Krzysiek Pawłowski just today. It's put in the archive, where we use this method to tell something about BEC interferometry, where we want to take into account, apart from single body losses, which is like natural to use in our framework, also 2 body losses. So something which is non-linear in a sense, which is a bit more tricky to do, but we hope to do it. And there is some outlook, what we are working on now. We try to also do something where the noise will be correlated, so not necessarily Markovian noise. But this is of course very difficult, but still, in our opinion, quite important, because it has relevance for models of atomic clocks, where you interrogate your atoms sequentially and you have some memory in your fluctuations of your laser. And we think that maybe you can tell interesting things using so-called matrix product operator formalism, and this is also something we are working on now. And the other extension of these problems is to go to multi-parameter case, which we are also doing at the moment, where you simply have many generators and many parameters and want to estimate all of them simultaneously. Okay, so this is take-home message, and thank you very much.
Okay, are there any questions?
talk to a pure mathematician, can it really be phrased in such a way that there are only mathematical structures all the way, and at the end there is a mathematical inequality that does not require any reference to things like estimates, etc., etc.
Okay, you have to define estimator, but this is a mathematical quantity.
You give a formula,
yes,
right?
Yes. So I gave you here this formula. What I mean by this variance of an estimator. This is the assumption of unbiasedness of estimator. Then I have the rule for probability. Then I have this quantum Fisher information, which is like optimization of classical Fisher information over all POVMs. Everything
and
is
this
rigorous.
is sort of tricky because what is the mathematical procedure that would give you the optimization overall?
Okay,
there is no algorithm in other way.
Okay, the proof that quantum Fisher information is optimization of classical Fisher information over all these operators, you can just give by constructing an example of an operator that saturates this.
Aha, so
you can
if you can find an example, then
I mean
you
can
solve the problem of.
I wrote at some point this formula for this symmetric logarithmic derivative,
yes,
which was like this rho a plus a rho,
yeah.
And actually you can show that if, in particular, if you take a measurement which is a projective measurement in the eigenbasis of this operator, you saturate this optimal bound of quantum Fisher information. So for this kind of measurement, so the classical Fisher information for the measurement which you take as a projective measurement in the eigenbasis of this symmetric logarithmic derivative gives you exactly quantum Fisher information.
So the assumption here is that A has an eigenbasis. That
it's Hermitian by assumption. Here it's assumption that it's Hermitian operator.
So that I was missing that.
The symmetric logarithmic derivative, we assume it's a Hermitian operator that saturates this.
Okay.
Of course, if it was not Hermitian, I would have to write a dagger here because otherwise the whole thing would not be Hermitian. And also we can define it like this, but then it's not really very useful definition because you can find it. Okay.
Any other questions? From the back? No.
So this is a great theory for Markovian system, but as we all know, recently experimentalists are using the other side, let's say. They are using multiple measurements, and they are using the fact that those measurements are leaving the footprint on environment. And from this, they are enhancing the estimation of the phase. Is it possible using the metrology language to take into consideration such systems? Or do you have an idea how to do it?
No, I think I don't exactly feel the example you mentioned.
So for example, you have an NV center, and if you do multiple measurement, there is...
Multiple, you mean one after another?
Yes, you are doing the measurement, then you are repeating the same experiment.
But you have the memory in the environment then.
Yes, exactly. So for example, the environment can polarize along some direction.
Okay, so within this formalism, it's very difficult to tell something general. So I would like to be able to say something, but I think that using these tools, I cannot.
Okay.
Anyone else? Okay, so then let's thank Rafał once again.